Okay, one last little piece in this unit. This unit that started with conservation of momentum in 2 dimensions, where balls collided and went off in different directions, and you had to do the conservation in the X and the conservation in the Y. And then it went to explosions, where they went off in all directions from being stationary. Then we did, is it elastic or inelastic of those collisions? And we went from that into conservation of momentum and energy questions, where there would be a collision and then the objects would stick together and continue to move, or one object would come down a hill and hit another object. And then after the collision, they would move off together. And then we did simple harmonic motion, which was really just with springs, conservation of energy with springs. And so the one last piece is a little tiny piece, and it's called the period of a simple pendulum. Simple pendulum is just a regular pendulum, like one that we would, what you would think of probably as a pendulum, where the pendulum ball swings up to its highest point, stops, swings back, swings up on the other side to its highest point, stops, swings back. So it goes back and forth, okay? In a way, this simple pendulum is kind of like a simple harmonic oscillator, right? It's swinging over and back, over and back. So it does look like a simple harmonic oscillator, where the linear force, so I'm just going to draw one side of it here. Remember, anything that undergoes periodic motion is a simple harmonic oscillator if it has a linear restoring force. So if we look at this ball, what would its linear restoring force be? Well, it has an Fg acting down, right? And so this Fg would have an Fgy acting in the same direction when it's up here, right, acting along the line of the pendulum. And it would have an Fgx, and the Fgx would be the linear restoring force, right? It would be what would be pulling it back to the center. So here, if we draw it on this one where the angle's bigger, this would be your Fg, this would be your Fgy acting along the line of the pendulum, and this would be your Fgx again, trying to get it back to the middle. If you look over on this side, here's your Fg acting down. So this would be your Fgy, always acting along in the line of the pendulum. And so here's your Fgx, this time trying to, again, acting in the opposite direction, but trying to pull it back to the middle. So if simple pendulum is a simple harmonic oscillator, then the Fgx is your linear restoring force. Okay, and so Fgx, if this is the angle theta, this would also be that same angle theta. And so Fgx would be equal to mg sine theta, right? Now, if you look at the sine theta in this triangle, we could draw a line over here like we did when we were trying to find the height. This would be the L, and this would be the x. So sine theta would be equal to x over L. And so that means then that Fgx would be equal to mgx over L. Okay? And we said that Fgx is like the linear restoring force. So remember that equation for linear restoring force is F equals Kx. So if Fgx is the linear restoring force, x would be x. That means mg over L must be like the k, must be like the spring constant. So k would be equal to mg over L. Okay, so now if you think of if this is like a simple harmonic oscillator, remember the period for a simple harmonic oscillator was 2 pi root m over k. So for a pendulum, if we're saying the pendulum, it doesn't have a spring, so it can't have a spring constant. But in the pendulum, then the spring constant would be equivalent to the mg over L. So this would be like 2 pi root m over mg over L. Dividing by a fraction is the same as multiplying by the reciprocal. So it'd be like 2 pi root m times L over mg. The m's are going to cancel, and you end up with the period equation for a period of a simple pendulum to be 2 pi root L over g. Okay? So to find the period of a pendulum, you need to know the length of the pendulum and the acceleration due to gravity. This is actually kind of significant in the sense that, think about, like, what it's saying is it's not dependent on the mass of the thing that I hang on the bottom of the pendulum. So I could tie a rope to the rafter in my classroom, and I could tie this pin to it, and I could begin it to swing back and forth, and we could time it, and we could count like 20 backs and forths, like over and back would be one cycle, and we could find the period. And that period then, we could calculate it. It should be equal to 2 pi root L over g, but we could also experimentally find it. So now I'm going to take the pin off, and I'm going to tie one of you onto the bottom of the string. And I'm going to swing it. And when I time it and count 20 times, the period, and find the period, it should be exactly the same. It doesn't matter if it's the pin hanging on the bottom or you hanging on the bottom. Now, that might not seem logical, but if you stop and think about it, the pin or you, one of you is going to take more force to get you swinging, right? But once you're swinging, the period over and back will be the same. It is possible then that everything would have the same period. Now you might also think, but wait, it also doesn't depend on how far back I pull it. If I pull it all the way up here and let it go, it's going to take the same amount of time to go over and come back as if I just pull it to here and let it go. And you might think, no, it should be quicker here. But if you pause and think about it, when you pull it all the way back, it's going to have a greater speed as it comes down, goes up, and comes back. If you only pull it to this spot, position 1, it's not going to have a very big speed to go over and come back. So it is going to end up taking the same time. So the higher the amplitude, the bigger the speed it has to go over and come back, but the amount of time will be the same. Okay? The different mass is going to require more force to move it, but the period will be the same. Okay, so the period of a pendulum, T equals 2 pi root L over G. There are a few fairly pathetic questions with this little equation on page 614. If you would do numbers 5 to 8, and then if you would also do the last two questions on the front side of your conservation of momentum and energy sheet, numbers 7 and 8. Okay, so 7 and 8 from the sheet, and 614, 5 to 8. The 5 to 8 will probably take you maybe 5 minutes because they're pretty pathetic. Sometimes you have to solve for L and they give you T. Sometimes you have to solve for T when they give you L. They're kind of rough, but you can cope. The chart for little g on other planets, I think it's page 133, because one of them asks you to find the period on, I think it's the moon. Okay, so the chart's on page 133. Very good.